So, now the turbulent intensity is increased. So, the relative turbulent intensity is greater than unity. In the first case what we have seen is less than unity, correct? Turbulent intensity is smaller, laminar flame speed is higher. Now, intensity I increase so that it becomes greater than unity. So, that in that ratio, for example, for the same range of the length scale ratio what we saw in the wrinkled flame regime. The previous regime, what will be the range of the length scale ratio? This is this same range what we saw in the wrinkled flame, in the same range you get this. But here the difference is the intensity, relative intensity is higher than 1, more than 1. So, flame lengths in eddies are established. So, this is schematic of this. So, you can see the unburned gas comes from this and burned gas leave here, and you have some pockets. What is, these are the pockets of unburned gas. Okay. So, here entirely is burned gas basically, but there are some pockets of unburned gas. Here it is totally unburned, and here also everywhere else is unburned, but you can see there are some packets of the gases. So, that means that the kinetic mechanism alone is not able to completely consume the reactants. So, the eddies are also contributing to that. Okay. So, flamelets in eddies regime, Damcol number is greater than 1 and have moderate value. So, Damcol number are not very high here, dA is not greater than, much greater than 1, it is only greater than 1, but have moderate values in this regime. Okay. So, you can see the flame, the pockets of unburned gases are present in the reaction zone. So, this is the characteristic of this particular regime. That means that the flame is not completely controlled by the chemical kinetics nor by the eddies. Both are going to be there to control this. So, rate at which these pockets of unburned burn and reduce in size. So, for example, this is larger and this is smaller. So, after this particular length thickness, you can see that only burned gas will prevail. So, here to the right of this thick line only unburned gas prevail. In between you can see pockets of this with both this is unburned gas and this is burned gas. So, both will be present in the in between this zone. So, how fast this packet is going to burn and also reduce in size will now depend on turbulent mixing rates and chemical reaction. Chemical reaction, but actually chemical reaction will play a role, but not a major role what it has played, it will play a lesser role. Chemical reaction will play a lesser role, but the turbulent mixing rates now will contribute to this regime. How fast this is going to. So, now in the previous case wrinkled flame there is no contribution by the turbulent mixing, but in this case the turbulent mixing rate is going to contribute to the this. So, you can see that the chemical reaction plays a lesser role, that means it is not completely gone, but it is going to play a lesser role when compared to this. So, when one more thing here, the Damcol is greater than 1, but there are situations where the Damcol number can approach 1, approach a value of 1. In this case the flame zone will become thicker and local flame extinction and the flame reignition is one of the important characteristics. For example, there is a gas which is gas packet which is trying to burn, it will extinguish and again it will be reignited. So, this type of a small instability will appear. So, we can see a flame will just put off and then again reignite at a particular point. So, that type of feature will be seen in this. So, in this case based upon the regime, the Damcol number is greater than 1 and has moderate values. If the moderate values is tending to 1, for example, at that regime if you try to operate, then you can see that the flame zone becomes thicker and local flame extinction, not everywhere, locally somewhere some packet can put off and then reignite. Unburned gas which is there in this flame zone can put off and reignite, and this can be observed. So, this is the second regime called flamelets in eddies. The third regime is called distributed reaction regime. Here the length scale ratio is smaller and that relative turbulent intensity is large, that is this. Okay. So, now we get the distributed reaction zone which is established. So, here what happens is the turbulent eddies, these are all eddies now, eddies of different sizes. So, you can see eddies of different sizes are present within the reaction zone. So, unburnt and burnt gas the reaction zone, and you see that tremendous amount of this del is greater than. So, this is the distributed reaction, del is greater than L naught. So, you can see L starting from the L naught, L lambda, L k, everything, every eddy will be there in this eddies of all sizes. Of course, L naught, L lambda and L k. So, all these eddies will be present in the within the reaction zone. Okay. In this regime, dA is less than 1, and therefore, reaction times are larger than the turbulent mixing times. So, that means that when eddies are present in the reaction zone, what happens is when the eddies break into smaller eddies and smaller eddy grow to a larger eddy and so on, you see fluctuations in the reaction zone. So, fluctuations in all variables like temperature, species concentration and the reaction rates, everything will be observed in this particular distributed reaction zone. Okay. So, reaction regime. So, here you can see that kinetics is contributing to small extent, but there are pockets. So, pockets of this, some smaller and medium size edges can penetrate into this, smallest to medium size edges can penetrate into this reaction zone. So, which will govern the conversion of these packets alone. So, basically outside of this the reaction rates are controlled by the chemical kinetics only, but in this case, the third case, only the eddies are going to take over the reaction zone, the thickness of the reaction zone and how fast the reaction takes place inside and so on. So, the fluctuations in all variables are observed here. In this zone, completely the reaction rate is taken over by the turbulent mixing, and we do not really care for the laminar kinetics, chemical kinetics in this. But in this case, both are important. Okay. So, where you can see this in the first case, the chemistry is very important. So, you have to use a chemistry to resolve this flame, and the interaction between the flow field and the chemistry will be basically we can see that when you predict the chemistry, that is only done by the chemical kinetics, and the wrinkling etc., when you resolve the flow field properly, you will get. So, the increase in the surface area and so on. But in the second case, there is a good interaction between, so you need chemical kinetics plus a model like say eddy dissipation model or eddy dissipation concept etc. are included. So, here say I say eddy dissipation model or eddy dissipation concept are used to, these are used okay, to okay. So, you can see that the eddy dissipation model or eddy dissipation concept are used to analyze the kinetics turbulent interaction, turbulent chemistry, you can say turbulent chemistry interaction. So, this is this regime where both are going to play a role, and this regime only eddies are going to take over here. There is no chemical kinetics requirement here, we can keep up of that and only use the eddy mixing rate as the chemical reaction rate in this. Okay. So, first one in this completely chemistry is very important to predict the thin flame zone, and so if you want to accurately predict the reaction zone thickness etc., we have to go for this. So, it is not a zero thickness. So, if you assume an infinitely fast chemistry or a single step chemistry, then you get a very thin flame zone. When you want to predict the thicker the accurate thickness of the flame zone, you have to use the chemical kinetics mechanism in this case. and when you resolve the flow field properly, you can predict the wrinkling. In the second case, we have to use chemical kinetics. However, we have to also take care of the interaction between the turbulence and the chemistry. So, that is this zone, flame rates in eddy. Third will be the zone where the chemical kinetics can be discarded, and only a model like the eddy dissipation model can be used to just predict. Mixing rate will govern the reaction rate here. So, these are the three regimes which are going to be observed in the turbulent premixed flames. And in the summary, we can see, when I plot a map of the relative turbulent intensity and the length ratio L by del, I know that this is a log scale, this is say 10. So, when this both quantities are less than 10, you get a regime which is laminar, which are phenomenally laminar. Then the wrinkle flame, as I told you, the turbulent intensity is very low, and for a given range of length ratio, I get wrinkle flame, very low turbulent intensity. So, now turbulent intensity I have increased to some level, but the same range of length I get this laminar length ratio, same range of length ratio, but some increased value of this. So, it is now more than 1, you can see. So, here a wrinkle flame, this ratio is less than 1, and in this flame this is more than 1, and to a particular ratio we get this flame rate in eddies. And we have a thicker flame. When I say, so in this case this is the damped chloride equal to 1 regime. So, here we get the local flame extinction and reignition. Okay. So, thicker flame zones are got. Again, this is also like this, it is not exactly the distributed zone. So, here also, so in this regime, it is also a laminar flame rates in eddies type of regime, where both chemistry and this are important. Okay. Now, if you increase the turbulent intensity and the scale ratio is decreased, you get distributed reaction zone. So, here also you can have a wider, somewhat wider, but it is when compared to the wrinkle flame or the flame and eddies, this ratio is slightly lesser, and we have distributed reaction zone, where we can see that the eddies are going to be inside the zone, and the eddy mixing rate will control the reaction, overall reaction rate, and the well-sealed reactor basically will be the, see for example, well-sealed reactor is nothing but where the reactants come in and there is a fast mixing of this, so that the reaction is complete and the products leave. So, such a phenomena will be there when the turbulent intensities are higher, then we can see that the flame will be completely controlled by the eddy mixing, the turbulent mixing. So, this is the map of the turbulent premixed flame regimes, and this can also be plotted in a plot called Damkohler number versus Reynolds number domain, turbulence Reynolds number domain. So, this is a very important diagram which will illustrate based upon the turbulent intensity, relative turbulent intensity and the length scale, what are the domains what we can have. So, that is the thing. Then we go for the next topic, which is nothing but the turbulent diffusion flames. Here the diffusion flames are analyzed. So, you know the laminar diffusion flame. So, let us also draw a laminar diffusion flame. So, it is a very well behaved flame, and basically the, I will just draw it. Basically, it will be longer, and you can see that based upon the flow rate, the flame length will increase. Now, here the characteristics, you can see this is the smooth surface, flame surface. Now, you can see the oscillations in the flame surface, etc. So, everywhere you can see the oscillations and other things, correct. So, the surface is now having lot of fluctuations. This is instantaneous images. Please understand, these are all instantaneous images. Okay, now this type of flames form when jet velocity, the fuel flow rate or jet velocity is increased beyond a critical value. Okay. So, this laminar flame will transition to this. Okay. Now, how it starts is, first we will see tip oscillations, only the tip portion will oscillate. The tip portion of the flame will oscillate when you cross this velocity, critical flow rate, and when you further increase the flow rate, the tip oscillation penetrate into this overall length, and finally the fluctuations are seen in the entire flame like this. Entire flame we will see the fluctuations. Very near to the base it will not be fluctuating at all, and but very near to the we can say almost the entire length will be fluctuating. So, this is the turbulent regime. So, important things what you can see is the turbulent regime, the Reynolds number is indicated here. These are all Reynolds number. So, 2700 to say 5700, you can see that the flame length does not change much. Flame length is not changing much, that we can see. Okay. So, the consequence of turbulence in the diffusion flame or non-premixed flame is a smooth laminar flame surface gradually transitions to a highly oscillatory turbulent flame, and basically as is shown in the instantaneous photographs. Okay. And also we can see that there will be some puffing and this. So, okay, you can see here some flame has just left. So, there will be some puffing, and due to the vortex shedding type of phenomena, the flame can puff and go off and again it burns. So, this type of vigorous oscillations are seen in the flame zones. So, other characteristics you will see. The first thing what we can easily observe is the smooth surface is not anymore there, and the flame actually is oscillatory. You can see that after a particular point this flame tip will move away, a lift off, it will lift off from this. So, that is also you can see the flame tip, but when they are attached you can see that there is a blue flame, bluish flame which is present in the base of the flame, and you can see that there is a again the same features like a luminous part here, and you can see that there is no smoke escaping for this particular Reynolds number range, but if you increase you can also see a smoke which is coming out of that and so on. So, the main characteristic is the tip oscillation which starts at a particular flow rate called critical flow rate, penetrates into the entire length, and the flame becomes oscillatory. These oscillations are contributed by the turbulence eddies of different scale into the mixing process. So, the non-premixed flame basically is set by a proper mixing of the fuel and the ambient air at stoichiometric proportions where the flame zone is formed. But if there is, if the turbulent flow field is present, the eddies will try to mix this fuel and air, and since the eddies are fluctuating, the mixing zone itself is fluctuating, and such fluctuations are important on the flame surface. So, contribution of the turbulent eddies of different scale to the mixing process will contribute to the oscillations. Now, molecular level of mixing, okay. So, that is the diffusion coefficient, molecular diffusion coefficient or molecular diffusivity will be enhanced tremendously, highly enhanced due to the turbulent eddies. So, this is the reason why we can see that the length is almost same. For a Reynolds number of 3000 to say 6000, you can see that the length is not changed much. This is actually when you take the axial oscillations are not much also here, only the oscillations in the surface are very high. So, you can see that almost if you take the average value of the flame heights here, it will be almost the same. It is not going to vary much. In the laminar regime, you can see that as the volumetric flow rate is increased, the flame length actually showed a very good increase. But here you can see that after increasing this to 2700 to 5700, you can see that the flame length has not much increase. You can see increase and decrease etc. for instantaneous. But overall, if you take average value of the flame height, visible flame height, okay, what you see in the photograph, it will not vary much. So, that means the turbulent eddies, they contribute to the mixing, and that does not depend upon the jet Reynolds number. That is what we saw. Okay, both the spreading rate and the axial velocity decay etc. does not depend upon the jet Reynolds number. So that means the turbulent eddies which are in the field, they are going to contribute to the mixing, keeping the turbulent flame length almost a constant, correct. So that is very important characteristic of turbulent flame length. In the laminar regime flame length increases, but turbulent regime flame length are almost constant. Jet flame, we are talking about jet flame here. So when you mix it, so the mixing process, the transfer process are enhanced to a high value. So significant increase in the mixing rates will contribute. So when there is a higher jet momentum coming out, okay, for the Reynolds number say 5700, you can see the mixing is also enhanced appreciably, so that the fuel is consumed within the same height. Okay. So the flame lengths as shown in the photographs are almost the same for a wide range of Reynolds number, say 3700 to 5700, 2700 to. Okay. So this is the range of Reynolds number which we have considered, and this has been seen by several researchers also. Okay. Now you can see that when you increase the fuel flow rate beyond this, the flame will be noisier. You see some noisy flame. Okay. And there is another critical flow in which the flame will lift off from the base. As I told you, here the lift off will happen. The flame will now stand. If this is the burner, the flame will stand at a particular height and burn. So we have already seen the instability, which is the only instability which we will observe in the non-premixed flame, that is lift off. So the flame lift off is observed in the same flame lift off is observed in the turbulent diffusion flame as well, and the flame will sustain at a certain distance from the burn exit. When you increase the flow rate further, you will get the lift off height will gradually increase, and finally the flame will blow off. Okay. So these are the characteristics of the turbulent jet flames. Now turbulent jet flame height, we have seen it to be constant. Let us do the scaling analysis. We have done the scaling analysis for the laminar regime, where we have clearly seen that the laminar flame height in the laminar regime is a function of basically QF. This is the volumetric flow rate of the fuel. Now in the turbulent regime, let us see how we are going to get the relationship between this. So now a turbulent flow, molecular diffusivity can be replaced by the turbulent mass diffusivity, that is D can be replaced to turbulent diffusivity, which is equivalent to, so we have already seen that the momentum coefficients are the same in a turbulent flow, correct, because it is controlled only by the eddies. So the fuel properties like this nu and alpha, correct, fuel properties in the laminar regime become flow property in the turbulent regime. So nu T, alpha T and dt, and so we can say the molecular diffusivity is nothing but the turbulent eddy viscosity. The nu T, or we can say rho epsilon, correct. So which we have already seen. So we can see, we can replace this to the eddy viscosity. So now what is eddy viscosity? We have also seen that eddy viscosity, as I told you, it depends on the turbulent mixing length and the turbulent intensity. So you can say Lm into V dash RMS will be nu T. Here I am putting here. This is the velocity, and this is the area. Okay. So this will be the so scaling analysis. So these are the factors which are affecting the flame length. Now if you take the turbulent mixing length, this can be of order of jet radius r. So this can be of order of r, and this velocity, the RMS velocity fluctuation can be as high as the jet exit velocity itself, VE. So the maximum fluctuating component can be of order of jet velocity. The turbulent mixing length can be of order of jet radius. So I can replace Lm by r and V dash RMS by VE. So this is also VE, please understand, this is also VE. So when I do that, then I get, so V or VE here I substitute, so this cancels and I get, so this and this cancels and I get R. So that means the turbulent flame height will depend only on the port radius. That is what we have also seen there. Okay, so where the turbulent case analytical solution, what we have seen here. So you can see that the epsilon is function of V E and R, and here also you can see that there is no, the velocity decay or the spreading rate does not depend on the jet Reynolds number. Please understand. Okay, for laminar jet the velocity decay directly proportional to Reynolds number, but for turbulent jet neither the velocity decay nor the spreading rate depend on the Reynolds number. It is not depending on the Reynolds number. So, so that is what here also we are getting. You can see that here the flame height is only dependent on the port radius. When you, if you want to increase the flame height, then you have to increase the port radius. That is what it is. So it is directly proportional to the radius. So nothing else affects that. So this is the actual curve. You can see that in the laminar flame, in the laminar regime, you can see the flame height with the jet velocity increases. Okay, and in the transition regime it drops basically to some particular value. Then in the turbulent regime it is constant. So now in the, this is the velocity, critical velocity, where the envelope flame starts flame oscillation. Envelope of the flame will oscillate now, and the oscillations penetrate. Okay, the oscillations penetrate to the entire surface. So when it becomes turbulent, almost all, this is turbulent regime, almost the entire surface will be oscillating. So envelope of start of the flame oscillations is this, right? The tip oscillation starts and penetrates into the entire length, and when it becomes turbulent, almost the entire flame will oscillate. Somewhere here the liftoff also will start. Somewhere after a particular flow rate, the flame will lift off. So if you say liftoff height will be 0 here, and after a particular rate the liftoff height will start. So this is the liftoff height. Okay. So these are the characteristics of the entire jet flame, where in the laminar regime you see a increase in the value, it reaches the maximum. After that the transition regime starts, where the flame height decreases as the Reynolds number or the jet velocity is further increased, and then in turbulent regime it becomes a constant, as we have seen, because only the turbulent mixing is going to take place there. The mixing is enhanced by it because it is present there. So the flame height variation as a function of jet velocity is shown for the 3 regimes. So this is very important to understand that the laminar flame height of the laminar will be function of QF. As QF increases or velocity increases, and keeping a constant burner diameter, velocity increases, the flame height increases. Transition zone it decreases, and in the turbulent zone it is almost constant. Okay, now Günther has given the correlation which is semi-empirical in nature. Some theoretical plus empirical experimental data has been used to arrive at the correlation for the flame height in the turbulent regime. Flame height of the jet diffusion flame in the turbulent regime. So it is LFT by D is equal to 6 times S plus 1 into rho E by rho F power 0.5, where D is the diameter of the fuel port here. So it is normalized with that. Then S is the mass based stoichiometric air fuel ratio. Please understand that in the robust correlation it was molar based, and in the Günther correlation it is mass based. So that you have to keep the difference in mind. And rho E is the fuel gas density, rho F is the mean flame density. So there the fuel temperature was used, oxidizer and fuel temperature. Here the flame density is used, and flame density is actually calculated as a mixture density at a temperature of around 1400. This is the average flame temperature. So at this temperature the mean flame density is calculated and used in this correlation. These are some values of some fuel, which is fuel jet coming out, methane, this. So irrespective of Reynolds number, correct. So why it need Reynolds number? Because it's only a constant, almost a constant. So methane LFT by D is 200, carbon monoxide is see very small, so the reactivity is high. Similarly, hydrogen also is smaller than this, and so on. So these are some of the values of the turbulent flame height by this. Okay, so like this, lot of correlations are available. So this I have just presented a simple correlation which is available for the turbulent flame height. Now, some notes about liftoff and blowout. Basically, you can see that the flame will lift from the attached position if the exit velocity is high. So exit velocity is high. Why it is? How can we judge the liftoff? Okay, and liftoff height, etc. That is what we are going to discuss here. So, but we have seen that the flame lifts off after a particular velocity. So, critical velocity is crossed, then we can see. So, it can also occur at a very small orifice, no, for 0.4 mm orifice which we illustrated earlier. Even in a laminar regime, the flame lifts off. However, in the turbulent regime, basically after a particular flow rate, the flame actually lifts off. And the liftoff height is the distance between the burner port and the base of the flame. So, partially premixed flame base. Okay. Then further increase in the flow velocity for the fuel will cause the blowout. So, that we have seen. So, now what are the criteria? Some theories to establish the flame liftoff. So, there are three arguments. The first one is the liftoff, the local flow velocity at the position where the laminar flame speed is the maximum, okay, that will match the turbulent burning velocity. So, that is the liftoff position. When the flame is lifted off, where it will stand? It will stand at a location where the local flow velocity at the position where the laminar flame speed is the maximum matches the. So, there is a position, there is a flame liftoff, there is a position. So, this is the base, basically base of the rim, the burner rim I can say, and the flame is lifted off here. So, the local flow velocity at the position where the laminar flame speed is the maximum. So, we can say V where SL is max, okay, that position. So, that X location matches the turbulent burning velocity ST. So, this will be equal to ST. So, there we can say liftoff, but this is actually complicated, correct. So, this is one of the theories. If we can come up with some theory or empirical correlations to get turbulent burning velocity ST and try to see the velocity where the maximum SL will occur, etc. Then if you can match this, then that will be the liftoff location. Okay. Then second concept is the local strain rate exceeds the extinction strain rate of a laminar diffusion flamelet. So, till this point what happens? Till this point where the flame has this, the local strain rate, that is strain rate can be a velocity gradient like this. Okay. So, a velocity gradient like this, something like that. So, this is strain rate. The local strain rate basically exceeds the extinction strain rate. So, this is greater than du by dx extinction, I will say extinction strain. That means at the strain rate surely the flame will not be anchored there. So, okay. So, this the local strain rate is greater than the extinction strain rate in this regime where I have circled, so that the flame cannot anchor there. So, in this position, in this position where the flame base is anchored, this will match. The local strain rate is matched, or maybe it will be lesser than the extinction strain rate. So, the flame establishes there. Okay. A simple theory is mixing caused by the large scale flow structures, that is eddies. So, these are eddies of odd products with the fresh mixture. Okay, when they mix is less than the time available is less than the critical chemical time, then flame will not be anchored there. So, this is the low resistance time we can say, correct. So, here time available for mixing caused by the eddies, large scale eddies, which mix the hot product with the fresh mixture. Why we need hot product to be mixed with the fresh mixture? Because it will auto ignite. So when the mixture when the mixture is formed, stoichiometric ratio, it should be ignited by some hot products, which are the already existing flame should reignite this, correct. So or the hot environment should ignite it. There is no pilot or anything there. So in this case, what happens is the flow structures which is actually causing the hot products to ignite the fresh mixture, the time available for that is less than the critical chemical time for reaction to complete to cause the ignition, correct. So there are set of reactions which will cause ignition. So the critical time to require for causing the ignition, chemical time, that is reaction time, that is the time available for mixing is less than that. So it is not able to mix properly. I will say low residence time for this, correct. The mixing cannot be complete within that particular time where the reaction rate or the chemical reaction rate is required. No, that time is actually more than the mixing time. So the products have not mixed properly with the fresh mixture to cause the auto ignition there. So these are the theories, but there are several other theories also which will explain the lift off and blow out. Basically, you can see that the mixture can be formed, but the mixture has a lesser time to ignite, or the mixture has a higher strain rate, or the mixture has see this the local velocity there is higher than the ST and so on. So these are the causes where the flame cannot survive and it lifts off, and further it goes and sustains at higher position from the base of the or the rim of the burner, so that it has this criteria satisfied, so that it will sustain there. After a particular flow rate, it will blow off. Okay. So now flame holding. Flame holding means how to. So we know that we want to burn more fuel in industrial applications. So when I go for high speed flows, I get the drift of instability in both the premixed and non-premixed flames. So high speed reactant entry or the fuel entry is unavoidable. So you can say take non-premixed, where you from the different ports you supply the air and the fuel, or you have a premixed turbulent flames which is high flow, high speed. Then you need to somehow control the speed where the flame can be held. Then so that means that you have to keep the flame at a particular location and allow that to consume the incoming high speed reactants, or the fuel and this fuel and the air should be mixed at a proper proportion to sustain the reaction zone. So there are several methodologies. I have given 3 methodologies here using pilot flames, a small pilot flame which will give extra source of energy to ignite the mixture. Then we can also have bluff bodies to create recirculation zones. Then we can have swirl generators. So for example, if you take some schematics what I have given here, so the reactant mixture comes in. So the reactant mixture goes through this port as well as from bypass ports here, so that it will have some time, extra time to go in and burn here. So you will see a flame which is coming out of this. So these bypass ports basically will create some time, and some reaction zones can be formed here. This will help in the sustaining the major reaction zone which is there in the front. Similarly, when the fuel plus air enters in, there will be pilot flame. So some parts, very small parts, say 5% to 10% of this can be of the reaction mixture can be supplied to the pilot flame port, where a flame will be formed here, and the incoming reactant will be burnt, ignited continuously. So the extra energy provided by the pilot flame will ignite the incoming mixture. So this is a typical non-premixed swirl flame. Okay. So here you can see the fuel comes from the core port, and air comes from the annular port, but this annular port has swirl. So either you can have a swirl vane here, swirl vane, and the swirl component can be imported here. So now if you see the structure of the flame is, the shape of the flame basically is like this. The flame actually goes and radially it enlarges, and as this shape basically, and you can see there will be two recirculation zones here. The one is the fuel driven recirculation zone, which will be like this, and the second one is the air driven recirculation zone, which is present here like this. Okay. So, there is a stagnation zone also in this. So, we can see that we can have a higher speed for fuel and air supply to this, and due to the stagnation region, recirculation zone, etc., you see the better mixing takes place. This is turbulent flame actually, turbulent. The swell component normally imparts a turbulence in the flow field. Okay. So, this the flame shape is actually represented by the mean stoichiometric contour. So, you can see that the flame is having higher radius, and because of the swell component, the tangential component, and it is sustained. Okay. The same thing can be done for a premixed also. This is for non-premixed, where the fuel and air enter from the separate ports co-flowing, but with swell component. We can also do the same for the premixed flames also. We can impart swell components. So, when I do impart swell components by swell generators or pilot flames, or we can have some bluff bodies to hold. See, you can also have a bluff body to hold this. So, if you have a flame coming out of this port, we can have a V gutter. So, this is called V gutter, and the reactants are flowing in this direction, and the flame will be held like this. So, this will be the flame basically. So, this is the flame. So, the flame actually will be anchor to this V gutter. So, because there will be recirculation zone in this position, so that that will reduce the velocity, and the residence time will be increased, so that the flame anchors in the V gutter, and we will get. So, bluff bodies can be used, this type of bypass ports can be used, and the pilot flames are used, or swell components can be used. So, when we have higher speed, then we cannot control the liftoff, etc. We have to use some of these techniques to do that. So, this is the turbulent flame characteristics.